Welcome! In this session, we'll tackle the problem titled Split Array with Same Average. It's an intriguing challenge that involves finding subsets of an array with equal averages. Stick around as we explore its complexity, approaches, and key insights. In this problem, we are given an integer array called nums, which contains n integers. Our goal is to determine whether we can split this array into two non-empty subarrays, A and B, such that the average of the elements in both subarrays is the same. To break this down, the average of a subarray is calculated as the sum of its elements divided by the number of elements in that subarray. For the condition to hold, the equation sum a/len a equals sum b/len b must be true, where sum a and len a represent the sum and number of elements in subarray A, and similarly for b. If it's possible to make this split, we return true, otherwise, we return false. The input consists of an integer array nums, where the length of the array is between 1 and 30, and each element is a non-negative integer between 0 and 10,000. The output is a Boolean value indicating whether such a split is possible. Let's look at some examples to better understand the problem. In the first example, the input array is nums equals 1, 2, 3, 4, 5, 6, 7, 8. The output is true because we can split the array into two subarrays, A equals 1, 2, 3, 4, and B equals 5, 6, 7, 8. For subarray A, the sum of the elements is 10, and the number of elements is 4, giving us an average of 10/4 equals 2.5. Similarly, for subarray B, the sum is 26, and the number of elements is also 4, resulting in the same average of 26/4 equals 2.5. Since the averages of the two subarrays are equal, the result is true. In the second example, the input array is nums equals 3, 1. Here, it is not possible to split the array into two non-empty subarrays with the same average, so the output is false. Now looking at the third example, the input array is nums equals 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. The output is true. This is because the array can be split into two subarrays, such as A equals 1, 1, 1, 1, 1, 1, 1, and B equals 1, 1, 1, 1, 1, 1, 1, 1. For subarray A, the sum is 7, and its length is 7, giving an average of 7/7 equals 1. Similarly, for subarray B, the sum is 8, and its length is 8, resulting in an average of 8/8 equals 1. Since both subarrays have the same average, the result is true. The problem also comes with a set of constraints and edge cases to consider. The constraints specify that the length of the array ranges from 1 to 30, and the values of the elements in the array are between 0 and 10,000. Additionally, the total sum of the array elements will not exceed 100,000. Edge cases include arrays with only two elements, such as A, B, where the result will always be false because both subarrays must be non-empty. When all elements in the array are the same, for example, 1, 1, 1, 1, the result is always true since any split will yield the same average. For arrays with large variations in values, like 1, 1000, 10,000, careful partitioning is required. Finally, when dealing with arrays close to the maximum length of 30, ensuring the solution is efficient becomes crucial due to the computational complexity. To start, let's consider the brute force approach as an intuitive but straightforward way to tackle the problem. The idea here is to generate all possible subsets of the array nums and check if any of them satisfies the condition of having the same average as the entire array. Once a valid subset is identified, the remaining elements in the array naturally form the second subset. The process involves several key steps. First, calculate the total sum and the length of the array. Then, for every non-empty subset, compute its sum and size, and check if its average matches that of the full array. While this approach is conceptually simple, it quickly becomes impractical for larger inputs due to its exponential time complexity, specifically O(2 to the power of n), stemming from the need to evaluate all possible subsets. This makes it infeasible as the array size grows, motivating the need for a more optimized solution. Now, a more efficient strategy can be developed by leveraging mathematical observations to reduce the search space. For two subarrays to have the same average, the relationship sum A/size A equals total_sum/total_size must hold. Rearranging this, we find that sum a equals size a asterisk total underscore sum slash total underscore size. An important insight here is that the numerator, size a asterisk total underscore sum, must be divisible by total underscore size for sum a to be an integer. Additionally, we can limit our search to subsets of sizes ranging from 1 to n // 2, since both resulting subarrays must be non-empty. Using dynamic programming, or DP, we can efficiently track the possible sums for subsets of different sizes. Specifically, we maintain a DP table where DP, k, stores all sums achievable with subsets of size k. For each number in nums, we update this table to reflect new achievable sums. Finally, for each subset size from 1 to n // 2, we check if there exists a valid sum that satisfies the condition derived earlier. This approach significantly improves efficiency compared to brute force. In terms of complexity, the improved approach has a time complexity of O, an asterisk total underscore sum slash 2, where total underscore sum represents the sum of the array, and a space complexity of O, total underscore sum, due to the DP table. To optimize further, we can incorporate early pruning techniques, which help reduce unnecessary computations. For example, if the total sum of the array is odd, it's immediately evident that splitting it into subsets with equal averages is impossible. Additionally, by checking divisibility conditions early, we can eliminate invalid cases before performing deeper calculations. Another optimization involves avoiding redundant computations by skipping numbers that have already been considered. These enhancements maintain the overall complexity but reduce the practical runtime by focusing only on valid subset candidates, making the approach even more efficient in real-world scenarios. The selected strategy combines the optimized DP approach with early pruning to achieve a balance between mathematical insights and computational efficiency. This hybrid approach significantly reduces the search space when compared to brute force while maintaining correctness. The reason for choosing this strategy lies in its scalability and practicality. Brute force, while simple, is intractable for larger arrays due to its exponential complexity. On the other hand, the optimized DP approach, augmented by pruning techniques, leverages mathematical properties to minimize unnecessary computations. Of course, this strategy requires additional space for the DP table and is more complex to implement than brute force, but these trade-offs are manageable given the significant performance improvements. By combining mathematical observations with algorithmic optimizations, this solution ensures both correctness and efficiency, making it the most suitable choice for solving the problem within the given constraints. To understand this problem, we need to determine if it's possible to split the input array nums into two non-empty subsets such that the average of the numbers in each subset is the same. The average of a subset is calculated as the sum of the subset divided by its size. For two subsets to have the same average, their sums and sizes must satisfy the equation sum1/size1 equals sum2/size2. Rearranging this, we get sum1*size2 equals sum2*size1. Now, if the total sum of the array is S and the total size is N, the subsets must also satisfy sum1/size1 equals S/N. This means sum1 must equal S/N *size1. Importantly, this implies that S/N must be a rational number for any valid splitting to occur. If S/N is not an integer, we can immediately conclude that no such split is possible. Therefore, as part of the initial checks, we calculate S and N. If S%n equals 0, it means S/N is not an integer, so we return false. Additionally, if the size of the array is less than 2, splitting into two non-empty subsets is impossible, so we also return false in that case. The next step is to formulate the problem as a variation of the subset sum problem. We need to find subsets of various sizes k such that their sum equals k asterisk S/N. Here, the target sum for a subset of size k is given by target underscore sum equals k asterisk S/N. Our task is to iterate over all possible values of k where 1 equals k less than n and determine whether there exists a subset of size k whose sum equals target underscore sum. This is a challenging problem because we need to consider all combinations of elements for subsets of different sizes. To solve this efficiently, we use a dynamic programming approach. The core idea is to use a 2D DP array DP k sum, where DP k sum is true if there exists a subset of size k with a sum equal to sum To initialize the DP table, we start with DP 0, 0 equals true, because a subset of size 0 with a sum of 0 always exists. For all other values of k and sum, we initialize DP, k, sum, as false because no subsets have been considered yet. We now define the transition process for the dynamic programming table. To update the DP table, we iterate through each number in the array nums. For each number, we update the DP table in reverse order, starting from k equals n down to k equals 1. This reverse order ensures that we do not overcount a number when considering subsets of different sizes. For each k and sum, we check whether adding the current number to a subset of size k1 can produce a subset of size k with the target sum. Specifically, if DP, k1, sum e number, is true, it implies there exists a subset of size k1 with a sum equal to some number. In this case, we set DP, k, sum, equals true, indicating that a subset of size k with the desired sum now exists. Finally, after populating the DP table, we check the results. For each possible size k where 1 equals k less than n, we verify if DP, k, target underscore sum, is true for the corresponding target underscore sum equals k asterisk, s/n. If we find a valid k, we return true, indicating that the array can be split. If no such case satisfies the condition, we return false. To implement this algorithm, we rely on two key data structures. First, the dynamic programming table DP, k, sum, is used to track whether it is possible to form subsets of various sizes with specific sums. This DP table is crucial because it avoids redundant computations by leveraging overlapping subproblems and ensures that we can efficiently determine the existence of subsets. Second, proper input validation is essential to handle edge cases. For instance, checking if s% is non-zero allows us to exit early when the average cannot be evenly distributed, and verifying that the array size is at least 2 ensures that splitting into non-empty subsets is feasible. In terms of complexity, the time complexity is O, n asterisk s, where n is the size of the array and s is the total sum of the array. This is because we iterate through all numbers and update the DP table for all possible subset sums. The space complexity is also O, n asterisk s, due to the storage required for the DP table. Lastly, we account for edge cases such as arrays with all equal elements, arrays with only 2 elements, and arrays containing negative numbers or zeros. These cases are handled either through prechecks or by the general DP logic, ensuring the algorithm is robust and efficient. The solution begins by importing necessary modules, itertools.combinations for generating subsets and math.gcd for handling common divisor checks. The function splitArraySameAverage first calculates the total number of elements, n, and their sum, total underscore sum. The main idea is to iterate through possible subset sizes I from 1 to n // 2, as subsets larger than half of the array would duplicate checks. For each subset size, the code checks if the sum of a potential subset, target underscore sum, is an integer by ensuring total underscore sum asterisk I, %n equals 0. If not, that subset size is skipped. If valid, the target underscore sum is computed as total underscore sum asterisk I, // n. Using itertools.combinations, all subsets of size I are generated and tested for their sum. If any subset matches target underscore sum, the function returns true, indicating that the array can be split into subsets with the same average. If no valid subsets are found after all iterations, the function returns false. Here, we start by importing Java utility classes and defining the solution class. The main method, splitArraySameAverage, takes an integer array nums as input. The goal is to determine if the array can be split into 2 non-empty subsets with the same average. We begin by calculating the total number of elements, n, and the sum of all elements, total sum. Next, the array is sorted to facilitate pruning during the subset search process. The for loop iterates through possible subset sizes, from 1 up to half the size of the array, since we need at least one subset smaller than the other. For each subset size I, we check if the total sum multiplied by I is divisible by n. This ensures that splitting the array into subsets with the same average is mathematically feasible. If the condition is satisfied, we calculate the target sum for the subset, which is equal to total sum asterisk I/n. We then call the helper method, canFindSubset, to check if such a subset exists with the given size and target sum. If the method returns true, the function immediately returns true, indicating that the array can indeed be split. If no valid subset is found for any subset size, the function ultimately returns false. In the helper method, canFindSubset, we aim to determine if there exists a subset of the given size with the specified target sum. First, we initialize a hash set called currentSums, starting with just the value 0. This set will track all possible sums that can be achieved using subsets of the array. For each number in nums, we create a new hash set, newSums, to avoid modifying the original set while iterating through it. We then iterate through all sums in currentSums, calculate a newSum by adding the current number, and add this newSum to newSums. After processing all numbers, we update currentSums to reflect the newSums that can be formed. Finally, we check if currentSums contains the target sum, which would indicate that a valid subset exists. If so, the method returns true, otherwise, it returns false after processing all numbers. This approach ensures we efficiently explore all possible subset sums while avoiding redundant computations. To solve the problem, we start with an example where the input array is nums equals 1, 2, 3, 4, 5, 6, 7, 8. First, we initialize some variables. Here, the length of the array, n, is 8, and the total sum of all elements in nums is 36. The next step involves iterating over possible subset sizes, ranging from 1 to n divided by 2, since subsets larger than half the array size would just duplicate the problem. For a subset size of 1, we check if multiplying the total sum by the size and dividing by n results in a whole number. Specifically, 36 by 1, %8 equals 4, which is not 0, so this size is skipped. Moving to size 2, we find that 36 by 2, %8 equals 0, making it a valid candidate. From this, we calculate the target sum for subsets of size 2 as 36 by 2, divided by 8, which equals 9. Now, we generate all possible subsets of size 2, such as 1, 2, 1, 3, and so on, up to 7, 8. For each subset, we calculate its sum, and eventually, we find a match. Specifically, the subset, 1, 8, has a sum equal to the target sum of 9. Since this subset works, we can split the remaining elements into a second group, and a valid split exists. Thus, the output for this example is true. In this example, we use a smaller input array, nums equals 3, 1. Starting with initialization, the length of the array, n, is 2. And the total sum of all elements is 4. Next, we iterate over possible subset sizes, which in this case is just 1, since n divided by 2 equals 1. For a subset size of 1, we check if multiplying the total sum by the size and dividing by n results in a whole number. Here, 4 by 1, %2 equals 0, so this is a valid size. The target sum for subsets of size 1 is calculated as 4 divided by 2, which equals 2. Now, we generate all subsets of size 1, which are simply the individual elements of the array, 3, and 1. Checking the sum of each subset, we find that the subset, 1, has a sum of 1, which does not match the target sum, and the subset, 3, has a sum of 3, which also does not match. Since no subset satisfies the condition, we conclude that it is not possible to split this array into two parts with the same average. Therefore, the output in this case is false. For this example, the input array is nums equals 6, 8, 18, 3, 1, 2. We begin by initializing the length of the array, n, as 6, and the total sum of all elements as 38. Next, we iterate over possible subset sizes, which range from 1 to n divided by 2, or 3. For a subset size of 1, we find that 38 by 1, %6 is not equal to 0, so we skip this size. Similarly, for a subset size of 2, 38 by 2, %6 is also not equal to 0, so we move on. For a subset size of 3, however, 38 by 3, %6 equals 0, making it valid. The target sum for subsets of size 3 is calculated as 38 by 3 divided by 6, which equals 19. We then generate all possible subsets of size 3, such as 6, 8, 18, 6, 8, 3, and so on, up to 3, 1, 2. Checking the sums of these subsets, we find that the subset, 6, 8, 3, has a sum equal to the target sum of 19. This means we can split the original array into two groups, with one group containing this subset and the other group containing the remaining elements. Thus, a valid split exists, and the output for this example is true. To analyze the time complexity of the algorithm, let's break it down step by step. First, we have an outer loop that iterates over possible subset sizes, denoted as I, ranging from 1 to n/2. This contributes n iterations since the loop runs approximately n/2 times. Next, within each iteration, the algorithm checks the validity of the target sum using the condition total_sum *I, %n = 0. This operation takes constant time, or O1, so its contribution within each loop is minimal. Now, for each valid subset size I, the algorithm generates all possible subsets of size I using itertools.combinations. The number of such combinations is given by the formula C, n, I, equals n. Slash, I. Asterisk, ni. When you sum up the combinations for all sizes I from 1 to n/2, the total number of subsets generated approximates to 2⁻n, which means this step is exponential in nature. Finally, for each subset generated, the algorithm computes the sum of its elements, which takes I, time for subsets of size I. Combining these factors, the subset generation and sum calculation dominate the time complexity, making it exponential overall. Considering the overall time complexity, the dominant factor is the subset generation and the subsequent sum computations. Together, these lead to a total time complexity of 2 to the power of n*n, which is exponential. This means the algorithm becomes computationally infeasible for large input sizes due to the rapid growth of 2⁻n. Now, let's examine the space complexity. The algorithm uses itertools.combinations, which is a generator. This means subsets are not stored in memory all at once, keeping the space usage minimal for this step. Additionally, since there's no recursion involved in this approach, we do not consume memory for recursive call stacks. The remaining space usage comes from a few auxiliary variables like n, total_sum, target_sum, and subset, all of which require constant space, or O1. Combining all these factors, the overall space complexity is O1, as the algorithm does not use memory proportional to the input size. When we compare this algorithm to a brute force approach, we can see clear improvements. A naive brute force method would involve generating all possible subsets of the input array and checking their averages. This would result in the same time complexity of 2 to the power of n*n, but would also require 2 to the power of n space to store all subsets in memory. In contrast, the current algorithm avoids this massive memory usage by generating subsets dynamically using itertools.combinations. Optimized approaches, such as those involving dynamic programming or backtracking with memoization, can reduce the time complexity significantly, sometimes to as low as n* total_sum. However, these methods often require additional space for memoization tables, which is a trade-off to consider. Looking at best, average, and worst-case scenarios, the algorithm performs best when a valid subset is found early, avoiding exhaustive checks. On average and in the worst case, the algorithm needs to test all subset sizes up to n/2, leading to the exponential 2 to the power of n*n complexity. The worst-case scenario occurs when no valid subset exists, requiring the algorithm to exhaust all possibilities. The exponential nature of the algorithm's time complexity can be mathematically justified. The factor 2⁻n arises because the total number of subsets of an input array is inherently exponential. This is due to the combinatorial nature of subset generation. The additional factor of n comes from the need to compute the sum of elements for each subset generated. Combining these factors, the overall time complexity is expressed as 2 to the power of n*n. On the other hand, the space complexity remains constant at 1. This is because the algorithm does not explicitly store all subsets or intermediate results in memory, relying instead on generators and a few auxiliary variables. As a result, the memory usage is not dependent on the size of the input array, making the space complexity highly efficient. When solving this problem, there are several common pitfalls to watch out for. First, it's essential to consider the constraint of equal averages. Many developers incorrectly assume that any subset can work, but in reality, the average of the subset must match the average of the entire array for it to be valid. To address this, always calculate and explicitly verify the averages. Another frequent mistake is testing all possible subsets without optimization. This brute force approach becomes computationally expensive as the array size grows. Instead, techniques like backtracking or dynamic programming can help prune unnecessary computations. Edge cases are another challenge. For example, arrays with duplicate elements, arrays of size 1, or situations where splitting into subsets is impossible can easily break a solution. Testing with diverse inputs, such as 1, 1, 1, 0, or 3, 1, 2, can help ensure robustness. Lastly, don't overlook precision issues with integer division when calculating averages. Integer division can lead to rounding errors, so use floating point division or adjust the formula to avoid losing precision. Another area where developers often struggle is with time complexity analysis. Misjudging the computational limits of a brute force or recursive solution can result in unoptimized code that fails on larger inputs. It's critical to analyze your approach and make sure it can handle arrays with sizes up to 10 to the power of 4 efficiently. From an interview perspective, optimization is key. Interviewers want to see how you can improve on naive solutions, so leveraging techniques like dynamic programming, memoization, or mathematical insights to reduce time complexity will make your solution stand out. It's also important to clarify constraints during the interview. For example, confirm whether empty subsets are allowed or how edge cases should be handled. Additionally, explaining your intuition is crucial. If your approach relies on mathematical properties, such as relationships between subset sums and averages, make sure to articulate why it works. Even if you begin with a brute force solution, discuss how you would refine it further, as this demonstrates your problem-solving process clearly. This problem shares similarities with other well-known problems, which can provide helpful context. For instance, LeetCode 416, partition equals subset sum, involves dividing an array into subsets with equal sums, a concept closely related to this challenge. Another example is LeetCode 698, partition to k equals some subsets, which generalizes the problem by requiring division into k subsets. Of course, LeetCode 805 itself is the direct problem we're addressing here. Additionally, LeetCode 39, combination sum, can provide insight into subset generation and backtracking techniques. Now, when it comes to alternative approaches, brute force is the most straightforward. It's simple to implement and easy to understand, but it becomes computationally expensive for large arrays, with a time complexity of 2 to the power of n. A more efficient option is backtracking with pruning, which avoids unnecessary computations by stopping early when certain conditions are not met. While this is an improvement, it still has exponential time complexity in the worst-case scenario. Dynamic programming is another approach that can be effective, especially for arrays with smaller values. It allows you to reuse intermediate results, making the solution more efficient than brute force or basic backtracking. However, it does require additional space and careful handling of state transitions to avoid errors. Finally, leveraging mathematical insights can be a powerful alternative. For example, you might use properties like the greatest common divisor, divisors, or rearrange equations to simplify the problem and avoid generating subsets altogether. The advantage of this approach is its potential to significantly reduce computational overhead. However, it does require strong mathematical intuition, and in some cases, it might not lead to a complete solution. Balancing these approaches and understanding their trade-offs is key to tackling this problem effectively. Great job following along. We've covered the key concepts and approaches to solving the problem of splitting an array with the same average. Remember to practice similar problems to solidify your understanding, and don't forget to stay tuned for more problem-solving sessions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!